Good morning, good afternoon, good evening, whenever you may be. It's another exciting science episode from deep in the Bretta bunker here in the quarantine, Southeast United States. Once again, it's another edition of ACE Academy, 8th grade science. I hope everybody had a great day yesterday. I hope you had a great day today. I hope you have a great day tomorrow. You guys need to stay safe, keep that social distancing thing going. We're getting close to the end of this thing, at least closer than we were before. So, love seeing everybody out there. Love seeing you guys' comments on things. Love making the fact that you guys are paying attention to this and learning some new stuff. Great seeing you guys when we do the live Zooms as well. Once again, make sure that attendance is set up by you posting in the comment section. Hey, I was here. Give me a big thumbs up and like the video, and hey, subscribe to the channel as well. Helps everything out in the end. Plus, you get a little notification when this thing actually goes live every day. So, 8th grade science, 8.E.1.2, hydrosphere. We're still playing around, and we're now down in the deep ocean. This is I can identify the characteristics of the deep ocean to make it scientifically interesting. So, when we talk about the deep ocean, we're talking about water depths in excess of 1,000 meters. 1,000 meters, meters 3.3 feet. So we're talking almost 10,000 feet when we talk about 1,000 meters. Once you get to 1,000 meters, there's no more penetration of any light or light energy. Temperatures remain around 39 degrees Fahrenheit. Pressure at the 1,000-meter level is 99 times normal air pressure. 99 times normal air pressure. That's a lot. Most of the world's oceans are significantly deeper than 1,000 meters. Continental shelf is just a hair under 1,000 meters in a lot of places. Once you drop off the continental shelf into the actual plains of the the ocean, the Atlantic's 5,000 to 7,000 meters deep for most of its area, except for the Mid-Atlantic Ridge and some what they call seamounts, where there's little outrisings on the bottom of the ocean. Pacific's a bit deeper with 6,000, 8,000 meters being the normal range. The Indian Ocean's 5,500, 7,500 range. So, easily basically 6,000 meters is a kind of an average depth of the deep part of the ocean. Now, the deepest part of the ocean over 10,000 meters. But at 6,000 meters, the pressure is nearly 600 times normal air pressure. I mean, again, because instead of air molecules being above you, you've got an entire column of water molecules, which are far more denser than air. So, I mean, you're talking about diving down to the bottom, down in these things. I mean, you have to create a vehicle that can withstand immense pressure of things, from the outside without crushing it. So, and like I said, so at the bottom of the deepest trenches, at depths in excess of 10,000 meters, the pressure is nearly 1,000 times normal air pressure. It's about like having a dump truck sitting on you, about 14 tons. 14,000 pounds, about 7 tons. That's a lot of weight sitting on, per square inch. So it's massively. I mean, you really can't comprehend what that feels like, having that kind of pressure on your body the entire time. So I mean, it's really. I've used scuba tanks up and down in 30 feet of water. It starts feeling weird. I can't imagine what it feels like when the pressures are way higher than that. So, to say the conditions on the bottom of the ocean are extreme is an understatement. So most scientists until about 1907 believed that life could not exist under such conditions. But then some scientists diving in the Galapagos Rift. So here it is. There's the Galapagos Islands. Here's Ecuador, Peru. Panama's up here. There's the Galapagos Rift, the Cocos Plate, and the Nazca Plate over here in the Pacific Ocean. Geez, it's about the same place that we get the El Nino surface temperature changes that give us El Nino and La Nina, literally right here in the Pacific Ocean off the coast of Peru and Ecuador. Well, that's kind of funny, but it just happens to be the same spot. But that's where it is. So guys were diving down there in a little submarine called the Alvin, and they ran into, first they found a hydrothermal vent, and then when they found the hydrothermal vent, they found things living around it in waters that, again, previously to that point, that nobody had imagined things actually could live in. They were living at the edge of the hydrothermal vent deep underwater. The discovery turned what scientists thought they knew on their heads. Organisms living in conditions of super high pressure, high temperature, no light, and toxic chemicals. So, I mean, everything we believe that, that like, all right, so if this stuff exists, you can't have life. Guess what? Yeah, you can. It just is different than what we ever expect, ran into before. Since this discovery, so they gave them the new title right there, extremophiles. So if you hear that, when you're talking about things that live in environments that are just totally out of this world as far as what we're used to, they titled them extremophiles because of the extreme nature of their living conditions. Since the discovery, scientists have found two different ecosystems at the bottom of the oceans. One is called, is based around hydrothermal vents, and the other one is based around what they call cold hydrothermal vents. Hydrothermal vents are exhaust ports for volcanic activity under the seafloor. Water from the bottom of the ocean percolates down through the permeable rock in areas where magma from the mantle is upwelling. The heat from the magma causes water to gain temperature. As it gains temperature, it has chemical reactions with the materials of the rocks that contain it. These chemical reactions make the water acidic and also puts these chemicals in the water as actual chemicals in addition to the water. As the water continues to heat, it starts to expand, creating pressure in the underground layers where it's flowing. This pressure in turn forces some of the heated water to find ways out. On the bottom of the ocean, there are holes in the rock that instead of draining the ocean like a bathtub are more like jacuzzi jets. And that superheated chemical-containing water is coming out under immense pressure. The temps in these things can reach 400 degrees Celsius, and the water is filled with numerous chemicals and material and minerals. This is what it looks like. They literally call this a black smoker. So it says these black smokers were discovering up, but then they continued to take samples that they found with them, and they found the area to be teeming with life as well. Microbes existed here that were not photosynthetic. They didn't need light to make their energy. They needed the chemicals such as hydrogen, sulfide, methane, and magnesium to perform their basic life processes. And where you have microbes, you have things that eat microbes. So instead of being photosynthetic, they were chemosynthetic. And why I don't have that written down in here anywhere. Oh, there it is. So chemosynthetic, which means they basically develop their life energy from chemical reactions, not from light reactions. And so when you have, microbes living and breeding and everything else, then you have the things that end up eating microbes, living and breathing and eating stuff, and so on and so forth. So you have clams, shrimp, mussels, and snails all feed on these things. You have these tube worms, you see pictures here. Fish, and then other predators that feed on those things. So some vent animals, such as tube worms and shrimp, actually host these microbes in their bodies and use the nutrients that the microbes excrete as waste as nutrients for themselves. I mean, it's more of a crab than a shrimp, is it? But it could be either one. And these things over here are tube worms. They can actually be a meter long, which is 39 inches. That's a pretty hefty size. So cold seeps are slightly different. But again, all of this activity is based on what they call chemosynthetics, which is the word that is right here. Chemosynthetic. That means that instead of being, like I said, photosynthesis uses light. Chemosynthesis uses chemicals. So these microbes use chemical reactions to make energy for themselves and live. So you have some that live around here, around these black smokers, which are, and again, so that smoke is just like volcano smoke, but instead of coming out as a gas, it's coming out basically as a liquid along with hot water. So that's what's coming out right there. And you see all the formations of things that are kind of developed. I mean, literally, that's not the seafloor. That's stuff that's building up around that hole. Microbes almost building like coral reefs around the hole, living off that stuff. Then you have cold seeps. Cold seeps are the other type of environment found deep in the bottom of the ocean. Cold seeps are different, discovered after the hydrothermal vent communities in this was discovered in 1977. So 6 years later, some guys ran into a cold seep in 1983, which is an area of the ocean floor where hydrogen sulfide, methane, and other hydrocarbons, oil, petroleum. So this stuff just comes out of the bottom of the ocean. Oh, imagine that. The earth just excretes oil into the ocean. It does. So hydrogen sulfide, methane, and other hydrocarbon-rich fluids, seepage occurs. Seepage comes out, often in the form of a brine pool. So cold does not mean the temperature is the seepage is lower than that of surrounding seawater. On the contrary, its temperature is often slightly higher, which is nowhere near like the temperature of the hydrothermal vent water. At a cold seep, the microbiome biome is chemosynthetic, just like at the hydrothermal vent, but the actual organisms are different species. Since the environment is extreme, the organisms that live there are very interdependent with many symbiotic relationships existing. So, stuff that lives at these things, again, first you have the microbes that live off of the chemicals, then you have the things that live off the microbes, then you have other things. So, here's another picture from a cold seep. And so it says the symbiotic, this is the name of the tube worm right there, Vestimentiferan, at 550 meters. So it's not as deep as that hydrothermal vent, but that's still pretty deep. Gulf of Mexico, down there, south of Texas, west of Florida, east of Mexico. And then the sediments around the base are orange bacterial mats. They live, these bacteria, these chemosynthetic bacteria live in mats. I mean, they literally just form these huge, looks like a carpet on the bottom of the ocean that are all made up of bacteria that are living in, producing their life energy from the chemicals coming out of the seeps. And these things, and this one in particular, are sulfur oxidizing bacteria. And then you have the shells of various clams and snails, which are also common inhabitants of the areas. I mean, there's some clams that have lived there and died, and their shells are just left there, and you have the worms that are still living there. So so you have again, this is one of those little short lessons, but you have hydrothermal vents where hot water is coming out of the ground, like volcanic hot water. And you have cold seeps where hydrocarbon-rich fluids, read that as oil, effectively is seeping out of the ground on the bottom of the ocean. Hydrosulfide, methane. Methane is the primary component of natural gas. So you have methane coming out down there. And again, where methane is coming out, it's a liquid because of the pressure. It's under such intense pressure down there that the methane it's not coming out as a bubble, as a gas, it's coming out as a liquid because of the intense pressure. And then there's these little bacteria down there that eat it. Imagine that, bacteria that eat oil. So that's kind of what gave us the idea that, hey, wait a minute. So if we spilled oil in the ocean, can we create a bacteria that will actually eat that oil up? And one of the things, back to when you spill oil in the ocean, guess what they do? They drop tons and tons of bacteria on it nowadays, and bacteria eat the oil out of the water. Yeah, just one of those things that they kind of figure out when they stumble across stuff on the planet. Neat, isn't it? Anyway, hey, little short lesson today, but an important one nonetheless. But so again, not all life is created equal, and is created here in the light of the sun. Some of it exists in places that again, scientists would have never figured that life would have lived prior to actually running into it. And since the oceans are 75% of the surface of the planet, and yet we've only explored like point something percent of them, we will continue to run into more strange and interesting things as time goes on. Once again, hey, like the video, leave a comment, tell me you were here for class, and sign up for subscribe to my channel. We'll see you guys next time.